Do you see it okay?
Yes, yes, Professor. It's visible.
Okay, good. So, so today we are going to focus more on cyber infrastructure for distribution system, some concept about vulnerabilities, and then introduce about cybersecurity, and if time permits, then maybe resiliency, but otherwise tomorrow about resiliency. So in this, we have talked about you have done four things: operation with DERs. See if I can. So we have done the operation with DER. We have done the distribution automation. You have done application control, application optimization. So this physical part is over, right? Now we are going to talk about only cyber, and then how we can apply AI for cybersecurity or rule based for cybersecurity, right? What data is needed. So cyber infrastructure and modeling and vulnerability is the focus today, right? Um, and we have to go back to the philosophy of operation and monitoring, and then we know that this is whole physical system, right? This line and distribution line, transformer, houses, everything is physical. As soon as we sense, it becomes a data, right, which is a measurement, and from there to all the way till we deliver the data to the control room is everything is cyber, right? Cyber is assisting physical system to operate better. And this cyber system is everything from sense to communicate to compute, visualize, and part of control. Not everything in control, because once we give the control signal back, it will be converted into a physical control, right? So if you want this generator to generate more power, you have to physically open a wall so it can inject more fuel. If you want hydro to generate more power, you have to physically open the water gate so it can there is more water falling on the turbine and it is generating more power. If you want gas generator or diesel to generate more power, you have to physically inject more fuel into that. If you want reactive power to be generating more, you have to physically change the field winding tap on the generators. So DR, again, you have to, the control is depending upon that what kind of power plant is control or what kind of, like DJ generator is also a DR if it's connected in the distribution system. But IBR, which is inverter based resources, most of the control is still digitally, right? Because let's say it's a PWM kind of control, right? So you can still do most of the control in digital world, and then the final will be the physical system because it's now injecting more electron. So once you come to the electrons flow, it is physical. Once you come to the data packets flow, it is a cyber, right? So let's expand on this part, which is all the way from sense, which is interface between physical world and cyber world. So this is where the physical world and cyber world interface, and then everything becomes cyber, and then we come to this control part. Again, there's another interface between the cyber world and physical world. So in this cyber uh, and physical world, this is physical system, right? So whole power grid infrastructure is a physical system, and it does not intersect with rest of the system, right? So this part is different. EMS and SCADA and communication and computer, all our communication and computer and power system is the one which is getting reflected into energy management system or ADMS or DMS or drums, and SCADA is the one which is feeding into EMS, right? So SCADA is again a part of this.
Sir, the screen is small size. Maybe can you enlarge it?
It is not clear, or it is
It is clear, but the screen is very small. Can you make it full? Or yeah, now
okay. Yeah, so this part, which is basically the power system, and computer system communication, it is interrelated, but it also has its own part. So computer system computing has its own, which does not intersect with communication. A power system, of course, has its physical world, which does not intersect with the rest of the system, right? EMS and SCADA is the one which correlates, because this is the one where you're taking the measurement and converting into a control, right? Of course, there are control which is also happening. We talked about distribution automation, has the substation automation, and then also feeder level automation. And some of those decision might be made right there at the substation level, right? So it does not come way all the way till EMS, but it is still a cyber system, because substation, you are putting a IEDs, which is taking the data and converting it to the physical. So then now, if you look at the whole infrastructure, right? So you have a substation, which is again physical, and that is where we put more and more IEDs, right? So sensor is throughout the feeder also, but substation is the one that is the first kind of data collection point, right? Things are changing now. We are putting some kind of data collection point at the pole also, but those are rare, right? So substation will be the one of the first point where we substation is the place where we put when the voltage is changing, high to low, low to high, right? And that's where we put the switch yard, we put a small control room, and then all these IEDs, and some kind of merging unit now, which was not done in the past. Merging unit is basically taking a lot of digital inputs and combining into not combining, but integrating that into some kind of digital format, so it can be transferred very easily, and then you can avoid electric wire, right? So merging unit is the way to avoid a lot of wires in the substation. The substation, you will have a sensor. A lot of these different sensors like CT and PT will be all here. Actuator will be here, which you can control. You can control the switch. You can control the tap changer. You can, so a lot of these control will exist. And substation is also tied with the generation substation, right? So the substation are different kind. There is one on TND, which is interface. There is one on transmission. There is one on distribution. There's one on generation, right? So actuator will be doing different thing. If it's a generation substation, then it's operating a generator, right? And a lot of automated control. So substation is definitely one of the large level of component in the power grid, where you are changing the analog to digital. Here, right here, we change that, right? It can happen at other points too, but substation will be the major part of the digital, analog to digital conversion. And from here, once you come to the, let me actually make this animation so it'll be easier. Are you able to still able to see the full screen?
uh, yeah, it's okay.
Okay. So substation we already talked about, and then within the substation you have this IEDs, or you know, RTU, remote terminal unit, and then this is like a cabinet with where you put IDs and some kind of server and networking devices. So this is where it should be in the enclosed room, so it's not getting impacted by weather much, even though these are open. But you put the sensor here, you put the sensor here, actuator here, but then wire it all the way at the same location into this small room. And this small room will have the cabinet and a lot of these IEDs, right? So IED and remote terminal unit will be, at the substation. And from here, you will have to have a lot of communication link so that you can deliver the data to SCADA master station. And then once you get here, then it's all about how do I visualize. So we already talked about control room in the past. And there, we are looking at several different things, but two things which is most important is alarm. These alarms are telling the operator that something is going wrong. uh, Remember that we are dealing with the human mind. We cannot give too much information. Every human operator has the cognitive limit. uh, there are different factors that we talk about when we talk about mind, that how can it process. One is that how to visualize so that they can see the data. Second is that thinking about their working memory. So typically it is, everyone is different, but in general it was found that 7-digit number is a good number to remember. And and this is why we call it that working memory is good for 7 digit. But if you go higher, it will be might be a problem. And that's why if you look at different numbers, that like phone number, typically it's a 7 digit, and then 3 digit of area code, right? And then it was combined into a 10 digit. So working memory is something that basically allowed to decide that what should be the how long should be the phone number. In US we also have SSN, and in India also you have a something like Aadhaar ID. So those are all based on that how many digits should be, because it depends on the working memory. If you make it too long, then people will not remember it. Other thing is about cognitive flexibility, which basically their ability to get trained and make a decision that they are not trained. So this is a whole new area of research, that how do you bring information to human operator. And this is all about cognitive engineering. It's not psychology, or it's not a power engineering. But power engineer has to be involved in this study, because without that we cannot tell that what data are possibility to display to the operator. So alarm is very important, because this is the one which we call attention span, which means that the operator will respond to alarm if it is controlled in a way that there is not alarm all the time. And if there is a lot of alarm, then it is already prioritized. So which means that software which is here need to do that alarm processing and prioritize it, and then send it to with different color or different priority to the operator. So now operator will understand it better, that okay, this is critical, I need to take care of this, right? And we already talked about the alarm could be anything. It could be thermal, temperature is high. It could be fan not working. It could be crew needs something, or it could be voltage violation. It could be overload. It could be generator, heating up. All these alarm will be coming here. One line diagram, which is basically the power system model. So, which means that EMS in the control room has to exactly has the same model which is in the field. And one line diagram will allow them to get into the substation and look at all the electrical connection. or the transmission line, which is once it leaves the substation, and then distribution system once, if you're talking about ADMS. So all of these is again a computing system. So in this part, there are a lot of IEDs, right, which is intelligent electronic devices, and these has either Windows is very rare, but Windows is also being used. So operating system could be Windows, it could be Linux, um, and then there is a hardware, right? So hardware, which is basically the microprocessor, then there's the operating system running on that, and then there has to be application because each IED is designed for something, right? So either it's a networking device, or it is a control device, or it is a sensing and phasor measurement unit, which is a PMU measurement. It could be RTAC, like which is a automation controller, which means that it can take the sensing or sensor measurement data, process it, and generate a control signal, right? So those are the application that will be running on that, and then it has to have a user. User could be the one which is monitoring the device, not often, but when it's needed. User could also be a vendor engineer, which is there sometime to see that there is no maintenance required for this device. And if something is wrong, I need to fix it, right? So they are basically a third part vendor, which will have some kind of access control. So it doesn't matter that which device we are talking about, which is uh, processing the data and at the substation, will have all these components: hardware, operating system, application, which is a software, and then user, right? And once you come to the communication, it could be a lot of different things, right? It could be microwave communication, it could be satellite communication, radio or wireless communication, fiber optic, or power line communication. Now, in the transmission, this fiber optic and power line communication is more common, typically the fiber optic, because we want the most reliable. So it's a costly but most reliable. Sometime, if the distance is not very high, we'll use the microwave also. Satellite is not very common, but like PMU, which is phasor measurement unit, it uses the GPS signal, which is of course coming from satellite, right? So anytime we need a GPS, it most probably it is coming from satellite. Remember that GPS can also be created by sharing through wire signal. So there are multiple ways to create the GPS also. Um, and there are different satellite system in the world, right? So US will have its own satellite system, and so that other country. And then there are also third party who can provide the GPS signal. um, GPS signal is typically strong if it is locked in into at least 3 satellite above Earth. If it is more number, it's better, but you need at least 3 satellite to triangulate the signal and have the very high accurate clock. Um, and then radio and wireless is not common in transmission grid, but it is common in distribution system. And then there is different kind of wireless signal, right? So now we talk about 5G, but there is a signal which is uh, a cheaper wireless, which is like, if you have heard about Zigbee protocol, is the one of the cheaper protocol for wireless, which is typically has been used for smart metering. So anytime communication we talk about, it could be different kind, and it could be different kind based on medium, based on protocol. Medium means it's wireless or wired, or and then what kind of signals it's acquiring, right? And then different protocol. So we have a lot of different protocol for communication data packet which will be built by these devices, software, and then how the data packet should look like when it's leaving the substation, right? So, so based on that, each communication link that we have, either it's from our home to a smart meter, from a smart meter to the data collection point, or from old war control device to the substation, from substation to the ADMS control center, from there to, if you remember the transactive energy that we talked about, the biggest project in Pacific Northwest that happened, there are so many communication link. And how we decide that what link is needed is based on the data, you know, data requirement, right? So what are the data requirements? So one is that, how much data we need to transmit from point A to point B, or point A to multiple point, which is called multicast. And the second is that what is the frequency? Do we need to send it every second, every millisecond, every minute, every several minute, or every hour, right? And all these are possible. Like, the smart meter can store the data, but only send it every hour or every day, every few minutes. So all these are possible. And then it depends on that how much data can be stored where we are transitioning to the next. Because if it cannot store, then of course you need to send it faster out from there, so you can delete that old data and store the new data. And then the last thing, which is the most important, is the cost, right? So fiber optic is costly, but it is more reliable, right? So if you build it, it will be more reliable. Wireless is is typically cheaper once installed, and more flexible, because you can, but at the same time it does bring like man in the middle attack possibility more, right? So when I say lost cost, it is not actually lost criteria, but cost is the most important when deciding, because everyone has to get as much as possible, but they always have a budget that, like, this is the budget, and if they cannot afford fiber optic, then I'll go for wireless, right? But the cybersecurity of a communication link, which means typically that what is the hackability or of different technology, and that becomes important. And we'll talk about that more and more, uh, you know basically today, and then also next week, most of the next week. This is only introduction to the cyber system, and then EMS, how to visualize, which is all about software, right? So this is all software, but it also has the same thing. It has operating system, it has a hardware where the things are running in the server, and then it has a user, which is operator, support engineer. uh, so this is all together is a cyber system, and then it comes with so many different constraint and different types, and get it is not being planned at one time, which means that something was added because there's a new wind power plant, substation, and now we have to put a new set of this small control terminal, which will have these things but slightly different because the technology has advanced. And then we have to think about, okay, what communication link now we are going to use, and then put it here in distribution system. If you're putting a distribution PMU, like I often get a question from utility who are going to install distribution PMU, what technology I should use, right? And then I start with that, what constraints you have, because unless we have the constraint, I want everyone to use fiber optic because that is more reliable, right? But with the budget, they might think that, okay, I'll go for radio because it's a cheaper. So all these technology are add on. It's all not done at the same time. And when you add on, you will follow a new set of devices, a new set of protocol maybe, and that requires us to operate different kind of protocol, different kind of operating system, different kind of hardware and application, which is software, and the communication link all together, right? So some is coming from microwave, some is coming from wireless, someone is coming from fiber optic, and someone is coming from power line communication, and then with the different protocol, all need to work together. So first thing that we do is sense, right? And we already talked about CT and PT a little bit, but we'll talk more. Um, One thing that is in sensing is that we cannot afford a high voltage, right? So we have a very very high voltage and high current in the transmission distribution system, and w- we have to use some kind of electromagnetic principle to lower the voltage down, right? So this is the very simple electromagnetic coupler, which is this is the wire carrying the current. If you just put it around, then it will introduce the magnetic field, which will cause the current to flow, and we can measure it. Number of turns is going to make this ratio, right, which is could be 500 to 1, 1000 to 1, or even higher. And this is how we get the potential and current transformer, right? uh, and we don't use the coupler all the time, right? Sometime we actually connect the high voltage side directly, and then the lower voltage, which is connected to the measurement, will have that kind of ratio, just like a transformer. So these two, we got to have that. This both are analog because it's changing the analog measurement to analog, but at the lower voltage and lower current. Then IEDs, with everyone from SCLG, Siemens, everyone make this. What does it do? It's basically a microprocessor, so it has the all the thing like this. It has a hardware which is a microprocessor. It has an operating system. If you want real time, then you probably need to go with Linux. If you don't want real time and you're okay, then you can go with the Windows. And there are multiple applications that what you want to perform there, right? Trend has been that before it was customized for each solution, each function. Now you get this, and then there is a slot on the back right here, and you can take out and replace it. And because of that, you can use the same device, which is the same microprocessor, but the function and interface is changing by swapping the basically your processor on the back. And you can use the same device for distance protection. You can use the same device for uh, you know like let's say over current relay, right? You can typically RTAC, which is automation controller, will collect the number of current and measurements from these protection devices or measurement devices, and can work like a microgrid management system, or can work like a relay coordination scheme. All those things are possible. uh, the main thing is that it all has a processor or multiple processor. It all has a communication link, which is kind of receiver processing, and interface for input, which is analog input. Or you can basically configure these system during the manufacture process, that you want how many analog, how many analog output, how many digital input, how many digital output. Like this one is right here, is kind of relay, and this says close and trip, which means that you press this button, it is going to send a signal command back to the breaker, and it will physically operate that, right? Of course, if the control command to the physical operation does not exist at the switch level, it cannot do anything, right? It can only send the signal. But you, in the circuit breaker, you got to have that all assembly with the switching and basically all the assembly that is needed to move the breaker to open or close, right? Which is whole spring and a lot of different things that exist in a circuit breaker. Phasor measurement will be also looking something like this. We'll talk about that. Switch status monitor, which is basically just looking at the switch and is it open or closed, and then sending that status. It can also look at the health of switches. There is also a fault indicator, which is typically cheaper. So these things range, in different cost. These two, if it is tied with directly to the high voltage, the cost will be the most high. So this is very very high cost, and then it will switchly drop the cost. Fault indicator will be probably the lowest cost, and then there are smart meter, which is also a different kind, but again it got to have a microprocessor. It has to have some kind of interface with the communication link, and microprocessor is basically has a software which is going to tell that what data packet and what format should go out once it measures, right? You still need a something like CT and PT to tie with the smart meter, so it can take those analog signal and convert that to a value which it can take and process, which has to be low voltage and low current, right? Well, as soon as you get to the digital electronics, you typically have 5 plus minus 5 volt or plus minus 10, right? Not more than that. So anytime you're dealing with the power grid, which has of course very high voltage, high current, you have to bring it down before you connect to the any of these IEDs, any of the PMUs, any of the you know uh, smart meters, and any of those RTAC, or like that we talked about. Now, sometime, most of the time, the electronics is rated for plus minus 5, plus minus 10, but some of the transformer which is installed here can take a little bit higher, like 110 or 220 volt it can take. Why? Because it need to interface, or it need to be powered by the a common power rating that exists. Second, it need to have enough power when it sends a signal out to a circuit breaker. And if you work only with the small voltage and current, it is not going to be enough power to move a mechanical device. So you have to have a transformer inside, which will take the high voltage, high current, and with some kind of processing to get to the low voltage, low current, and then again, the same amplifier will take it to the higher, and then give it back to the some of the control device, which requires a little bit more power. So that can exist, and those are the rating that we need to choose when we are buying these kind of IEDs. So phasor measurement unit, which is one of the most newest sensor, as the name says, I always say that it's not a phasor measurement, but it's a phasor estimation. Why? Because it you to measure the phasor accurately, you cannot determine the phasor. So what is a phasor? Phasor is basically the rotating vector, right? So voltage and current, these are all signal, right? It's not a one point. It is varying with the time. It has a direction, and it is rotating. And because it's so basically voltage and current is a phasor. So phasor is rotating and creating a sinusoidal wave. If it's a perfect AC signal, of course DC does not, it is not a phasor, right? So AC signal, uh, which is rotating with a certain direction and certain relative angle, is all the characteristic of the phasor. So now if you want to measure the phasor, we need to know the magnitude, we need to know the angle, because it's always rotating. So if I say that, okay, tell me phasor now, right? So you basically kind of freeze the phasor at that time where it was, and at that time t, you will say that you have to have a reference, and you say that from reference it has rotated 10 degree, or you will say that it has rotated 360-degree, right? And once you rotate the 60-degree, then you are at the same place where you are, right? So that's how a sinusoidal signal completes the 360-degree two cycles, and then start again. It repeats the same thing. So with that phasor, if you want to measure, then we have to measure the magnitude and angle also. So, and then we also need to rotate. You need to find that how fast it's rotating, right? So it needs to know the frequency measurement and the phasor magnitude, and we need to do that for one or more three-phase voltages and current, right? Again, it has to be AC. A lot of different PMUs exist. Distribution PMU exist also with several different manufacturer. One of the manufacturers, which at least in US is probably more, is PSL, micro PMU. So single phasor and frequency values, has to meet certain standard, and the standard was C37.18, and that came in 2011. It was revised in 2018, and then there was a lot of more C, like this is point one, which is about electrical parameter, and then point two is about communication. So this point one is about the electrical. So it should stream the real-time data output, and that's why it needs a GPS signal, so it can measure that where you are when you're rotating, right? So it determines the frequency. Of course, PMU itself we can talk several days, because there are so many fundamentals, filtering process. How does GPS signal get converted? What is the PLL, which is the phase lock loop? Why it's needed? How the filtering is done? You can talk about a lot of different things, but the essence here is that it takes the analog input, which is CT and PT, and gives you digital output, which is the phasor measurement, with voltage, magnitude, with angle, with frequency, and in a standard format, which is 37.118, and in real time, which means that it can report uh, fast enough. You can, there are some PMU which is reporting 200 times per second, and then there are PMU which is reporting 30 times per second, 60 times per second. So, which is probably the fastest uh, reporting device in the power grid, right? Now, in terms of sampling, there are other devices which is even faster, like let's say relay, right? It's really sampling fast, and this is actually built on relay. When it was first invented, Dr. Arun Fadke, right? I mean, he was the one who was inventor of this PMU with Dr. Jim Thorpe. So when they invented, they actually build it from the protection, and you can compare a lot this, like earlier, before PMU we used to have like a snapshot pictures, and then after PMU we have uh, not a very high resolution, but good resolution video, right? So why video? Because now you're recording that how my voltage and current is varying, more like a video instead of snapshot pictures that you were taking before. One of the, which is a former CEO, Terry Boston, he says, like, it's like going from X-ray to MRI of the grid, right? So it basically gives you a higher visibility in terms of high resolution, but only if you have everywhere. So a little bit more about CT and PT, right? So how it looks like and how it's connected to the PMU. So you have a potential transformer, and it will have a lot of these things because it is connected to the high voltage, right? So high voltage, it is applied on the primary side, and then the secondary side, it is uh, very low, which is, like I said, that 1000 to 1, 500 to 1 ratio. It is coming here, uh, and the ratio is decided that, what is the high voltage line, right? So if it is 132 kV versus 500 kV, or even higher, you have to increase the ratio so you can get the lower voltage and low current out, and then apply certain burden, and then attenuator, and then give it to the PMU, which needs analog input from voltage, and then it also needs analog input from the current. And this is a current transformer, which means that it has to be connected in a series with the high voltage conductors, right? So in series, so that it can measure the current, and then same thing, and then you get the low voltage with the very high ratio of similar to this, like 1000 to 1, 500 to 1, with a burden attenuator, and you feed it to the PMUs, right? And then we get, what do we get? We get the phasor, and you have to feed with the GPS. It also gives you sequence voltage and current, phase voltage and current. It gives you frequency. It can also tell you trade of change of frequency, right? Because it's, you got the frequency at this time, t equal to, and then after a few milliseconds, you also got the new frequency measurement. So it can give you rate of change of frequency. Typically, it's not very good. It depends on the algorithm and technology, but once we go into the mathematics of how it's being converted, you know, calculated, we will know that it's not very good. It can also, because it's a sending data packet, so you can add more input and put that into a data packet which goes out. So you can take the circuit breaker switch data, which is a digital data packet, and put in a user defined bits. So C37.18 has a is a data packet, and data packet could vary in size, and it has to have a certain format. So the first four bits, what would look like, next two bits, next four bits, next three bits, it has a format, right? So so when you think about current and voltage in the power grid, we always think about electrons flowing, right? In a cyber world, we have to always think in terms of data packets, and data packets goes in chunk, right? So one data packet, then another data packet. How often it's going, that's what we need to decide, and fix it based on requirement. Other sensing is a smart meter. uh, there are different kinds. So electromechanical meter was, of course, from long time that we used. Then came the solid state digital meter, and then finally we have this integrated next generation meter. There is a difference. So electromechanical that we used to have, and still there are Sarah, is typically low accuracy. It is expensive add-on communication, and we cannot send any control, because that's a problem of, if it's analog, it is not flexible. You cannot just control on the fly by changing the software or by changing the operating system. You cannot do that. But in a microprocessor, you can say that software version 1 now will be software version 2, which has more function, right? And that's why if you have your laptop or computer getting updated, sometimes you get more features in your phone because the software update has been done, or more features in your Windows because software update has been done. You cannot do that in analog electromechanical meters. Solid state came with a little bit high accuracy, but there was add-on communication and limited control, right? And the next one, which is a fully digital, has, of course, high accuracy, integrated communication, and also control, which is a good part. So now, if you go into the computing device, we already talked about it has to have a hardware, it has to have a software, and it has to have a user. Um, each of that computing device, if you further expand it, it will have a system bus, right? So system bus is basically, you can think about like open interface where you will talk to with any other smaller unit, which is like a CPU, right? Central processing unit, disk, which is going to do the memory, the network, which will talk to this, this interface, and keyboard. The system bus is going to take the data from one location and transfer it to second and to the another one, right? So keyboard, like my mouse is moving, so this is also talking with the system bus first, and then from there it is talking with my screen, and then it's talking with the network, and network is talking with your network with multiple hops, and that is how you're seeing the slide and even the my mouse movement. Okay, so everything is happening in real time, right? So it's just like amazing. I'm going here and you were able to see it, but there's so much going on inside in processor to make it happen. And all this server, which is, my internet connection is different provided by my university before it hops on into the next and then before it reaches to you. So system bus, which is, sense, control, address data between components, is kind of interfacing all the different component in that computing device. CPU, you can have a different kind of processor. uh, some more example, x86 or ARM. Of course, we keep seeing the cost going down and performance becoming better. It will also have some cache and some registers, all the inside that is you typically expect from a microprocessor to have. And you can have multiple, right? So it's not a single, but it could be multiple core and everything is possible. Memory, you can have a primary memory system or you can have a double, and you get to have memory management unit, which enables the virtual memory. Network is basically is a communication medium which you have to have an interface, and also all of these needs a driver. So disk driver is a software which is interpreting the disk command into the system bus so that others can understand. um, Network is also comes with the same thing, drivers, interface which you install here in your computing device, and the network that you can plug in into the terminal unit that is saying that, okay, this is for Ethernet communication, this is for HDMI communication, and this is for whatever you want, like USB communication, right? So different kind of interface and networking that you need to have a pin, which is hardware. You have to have a software, which is a driver, to understand that what is being plugged in. And then once you plug different things, either it's Ethernet or it's a USB or it's a uh, you know a very old way of doing things, which is you know some, like a 16 pin and 18 pin, 21 pin kind of that you connect like a printer, right? So those are uh, you know different way of doing the communication. As long as you know that how many pins are in the wire or how many digits I need to send, uh, which will be translated from this interface, we can communicate with the network. And then input output, which could be additional like a USB, monitor, mouse, printer, etc., will be connected here. Then comes the operating system, which is the core, right? I mean, which is driving the whole thing. And this operating system, you know, uh, again, I'm taking example of SEL. Of course, it could be G, it could be Siemens, or it will be running, either Linux or Windows, right, or Unix. So different possibility. Like I said, that if you want real time, you have to learn the Linux or Unix. If you want non-real time and more user friendly, then you run Windows. Sometime we have the ability to run both and switch between those as needed, right? Because it can entertain that. So manage and abstract of computer hardware, which is the processor, memory, network devices, all of these that is connected right here. We have to manage these, and this is managed by the software operating system, which is installed a part of the CPU. So you can take this, which you call kernel, part of this processing unit, and then you will put the operating system into that, which you cannot overwrite easily. And these operating system will interface with applications which is running on top of this, which is entertaining the users or programs. But operating system will have all these processors, memory management, networking, system calls, scheduling, interrupts, and you have to tell that how much and how many networking interface are there, because then only it will configure it, right? And then other hardware, which is processor, memory, network devices, all these things will be also interfaced with the operating system. So different function, it can do system calls, where user program can access, can do the memory management, can do the process management, networking, of course, we already talked about, which is low level networking function, and file systems, right? Which need to be managed also. And then security. So security, that's where we'll spend more time. Access control, that who can access this operating system. It is very important because it should not be allowed to everyone. And if someone is going to access, how do we know that it is a person who should have that access control? So how do we authenticate? Either it's a double layer of password, or it is another way of doing that. But authentication is very important. And then we also need to audit that who went in physically, and all the log files, that who was able to access digitally. So when we audit, we can see that okay, this person does not look like IP address that we allowed for access, and then we can track down and basically know that something has been compromised. So all of these are part of the computing system, but at the same time, it is important to understand that it you know everything is being done with the data packets, and these data packets at lower level is basically a signal in terms of 0 and 1, right? So those are the bit, and how many bytes, and our operating system is entertaining 64-bit computing, or it's a 16 or 32. 16 is long gone, but now we have 32 and then 64-bit, right? And now even higher. So all of these processing is lower level is still happening in 0 and 1, which is this is how electronics work. Networking, we talked about microwave, satellite, radio, wireless, fiber optic, power line communication, but it is different thing is chosen. Like we already talked about, transmission will have a different preference for fiber optic is most common, uh, PLC, which is power line communication, and then microwave, satellite can also be used. We will have all these things: generation, wind, offshore, high voltage substation, and then between high voltage to high voltage substation, and then sometime talking with the lower distribution system, right? Your GPS is based on satellite, and then cellular or wireless is based on the cell tower. And then we also have distribution, which is could be fiber optic, BPLC, satellite, Y, which is WiMAX is just wireless, but a little bit higher end of wireless. And then several different variation of that, GSM and all those things. As we do this distribution, connection, this is between different remote terminal unit, uh, medium voltage substation, and then basically in between or with different component, which is large building, or e-cars, or or photovoltaic, or even some building with cold storage. Once you come to residential, then it's typically wireless, which one variation of wireless, and becomes cheaper too, right? Sometime, very very crude way, which is DSL, which is digital subscriber link, and like a dial-up connection too. Now, if you go and look into a little bit about network architecture, right? So you talked about sensing, you talked about software and hardware, The networking is the one which is taking the data from one location to another location, right? And there is a lot of different protocol. One is Ethernet protocol, and all the data that is flowing even now, like I said that my mouse movement on my slide and your ability to see my slide is actually driven by TCP/IP. So how does it work? It has a four different layer, um, and sometime we also have a seven layer model. We are talking in terms of simplification. You can, if you are more interested, you can look at the seven layer model, which is OSI seven layer model. In a simplified way, four layer model. It has a link, which is basically a physical link. So it's either Ethernet or Ethernet 2.11, uh, which is basically communication over some network, uh, media access, local addressing. This is all comes into the link part. And link has to be established first before you come to the internet part, which is interconnection of network into internet. And this internet layer is basically specify the global addressing, routing. It will have the IP address and all this ARP address like that. Then comes the transport, which is basically the TCP UDP. The difference is that just the way we handle it. So in UDP, if the data packet is, there's a lot of differences, but the simplest difference is that if the data packet is lost in UDP, you don't search for that. You don't wait for that. In TCP, you actually look for that till certain time before you say that okay, it's lost. So data packet is leaving from point A to point B. It's not necessary that it will always reach there, right? And that's why sometimes you have a slow network, you have some other problem, right? This is only one of the reasons that it might happen in that way. And transport layer, we talk about process to process communication, which is flow control and reliability of uh, connection. And then finally on the top you run your application. So when you open the internet and you type HTTPS or HTTP, that is the application that is running on top of that, using all of these things, right? So uh, this all came by ARPANET, which was one of the in 1917 US, and that's how internet was discovered. And then a lot of things has been done to make it secure, to make it high efficiency, and different kind of protocol that comes with that, and then layers of abstraction. So again, very quick overview because we cannot go in a lot of details in these many days. But the way why it is important to understand the different layer, because the attack that can happen can also utilize the vulnerability in different layer, right? For example, they can spoof the IP, and that is the internet layer, right? So it is important to understand if you are really going to get into detail of a different attack possible and which kind of vulnerability was utilized. We have talked about this several times. Just very quick that this management with the SCADA, start with very lower level appliances at home, and that is device power management. Then we get to the home management, which is home energy management system. Then we can get to the building energy management system. Then bigger than that will be macrogrid energy management system, which is campus neighborhood. And then we get to the distribution management system, and then finally transmission level energy management system. Of course, nuclear power is not written here, but there will be same layer. And then you come to the very large interconnection or even country, and that is a wide area energy management system, right? So let me take a 5 minutes break, and before we take the break, we can do some answer. Q&A. Let me look at that, and then we'll continue.
Yeah, that is okay.
So, any questions so far? It's a lot of information, short time.
Yeah, sir. Good morning, sir. I had one question that if we are, if I'm using any test bed, real-time test bed, so
Hmm.
what is, so what should be the SCADA? So what should I use for as a SCADA? Any software or what is it actually in a test bed?
Yeah, so there's a lot of possibilities. Either you can use industrial software. Remember that SCADA is only going to work once you already have a sensing and some kind of communication, right? So SCADA is a software which is basically going to collect information and the network, and then uh, store in and make it ready for management system, right? So SCADA does take data from sensors, then use the communication link that has been installed, and then it might align the data with certain kind of clock protocol, and 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 it integrates all the data together, and that's what the SCADA software does. So there are industrial solution. If you're not going with industrial solution, then you have to build your own, which will
Yeah,
take this set
can
of
I build
data.
it with
And
my own IoT device like any Raspberry Pi device or Arduino device?
yeah, so that will not be if you want to implement SCADA using Raspberry Pi, it will not be equivalent to what exists in the field. It might be equivalent to something uh, what is at the building level. So if you want to build a building management system SCADA um, using Raspberry Pi, then it's at the same scale, right? Which is basically collecting multiple measurement from the building with the communication link, and then aligning it, which can be done in Raspberry Pi with certain kind of clock, because Raspberry Pi also has its own clock if you can connect it, and then it will represent that, right? In some way, you can basically Raspberry Pi is basically going to represent a computer which is a SCADA computer, which is a multiple computer or server, and that's what it's going to represent, right? So if the number of measurement is in within the limit of that Raspberry Pi can process, then yes, it can it can represent in some way. Remember that any modeling and simulation that we do, there are hundreds of ways to do that. We are always trying to when we try to model and simulate, we are always trying to capture the behavior, and the capturing the behavior is not only one way of doing that. You can uh, say that I want to capture the behavior 1 and 2 and 3, and then I want to exactly do the way real field is doing, right? And then but still emulated. And then you want to say that, okay, if the only way that you can do actual behavior is by replacing that with the hardware in the loop. So when we say that we are trying to model SCADA, we are trying to model the actual behavior of the system, RTAC, or anything, we always look at that what I want to model, which behavior I'm trying to imitate, and we focus on that because that requires limited resources. And if you want to model, with 99% accuracy, then you need much more resources to do that, and then it will represent multiple different kind of behavior that is possible. So when we say that modeling and simulation is possible with a certain thing, you can model with the MATLAB, you can model with this. We are trying to just capture one behavior, and there is some difference between simulation, emulation, and real time. Simulation is when you start sending data packet, It is emulating because now the data packet is actually flowing. Simulation does not need to have a data packet. It is only directly, giving you the information. So that is simulation. And then if the emulation is going to real time, then it is more closer to reality. But if you represent and replace the some of the component with the real hardware, then it is more closer. So all of these are possible. uh, one and we can do a lot of analysis also if we know our limitations.
Thank you, sir.
Okay, so
So I had a question.
mhm,
So as you said that we need to use some, I mean, Linux or something to make it the real-time test bed, right? To
mhm.
make that thing a real time. So can't we make a real-time test bed using the Opal RT? Because Opal RT it will run in the Windows.
Yeah, so OpenRT is actually real time, because it is electromechanical
Yeah.
simulator. And OpenRT, if you can interface with either emulation, because now you cannot do the simulation because you need actual data packet to interface with OpenRT. So in that case, any hardware like a Raspberry Pi will be more useful because then you can directly interface with the OpenRT if you're trying to imitate home energy management system or something or IoT. Uh,
No, not for that, sir. My question was like, basically, if we want to make the real-time test bed for the detection of some algorithm, like of
mhm.
some attack, so can't we make it with the Opalati?
It depends because OpenRT is only going to simulate your power grid, right? So if you want a cyber, then you have to buy additional software, which is software uh, from OpenRT, right? Which you can simulate your cyber component. But if you want a real attack on a hardware, real cyber device, which is like RTAC, or you have to have those things, and you have to have a channel to attack those, right? If you want to represent impact of a cyber attack on the cyber system, which you are modeling, and how accurate you're modeling, it depends on that. Then you can do that with OpenRT because OpenRT with cyber software simulation, right? Without cyber, so OpenRT also sells. They have collaborated with one company which makes the cyber networking simulation, but it does not allow you to do the cyber attack because it's still a simulation device. It is only doing real time simulation. There's no emulation there. Then once you put the interface from OpenRT, which is like they also sell interface, like it is like C37.18 interface, DNP3 interface. So once you buy that, then now we can send the data from OpenRT to another device. Now that device need to be hardware or software which will receive this signal, and then you can do some kind of cyber attack on that hardware which is external, or that software which is external to this OpenRT, because now it's receiving the signal and sending the signal back.
Okay. So, like just testing the detection algorithm, like
Mhm.
if we are manipulating some data and then taking it back from the relay, from SCL relay, and then testing that algorithm, can we do that in the
Yeah,
Opalati?
so that's what I was saying, that everything is possible with as long as we understand
Communication.
the limitation, as long as we understand the limitation, right? So simulation, which is OpenRT is simulation, it is possible to imitate the behavior of which you need to model, right? You need to model that if this attack happens, how it will impact the cyber and physical. You need to model that. Once you model that, then you can detect because the behavior has changed also. but it depends on the modeling of impact of attack, which you need to uh, do a good model and good simulation of that. Second is the behavior model, right, which is actually you're sending the data packet out and then putting in another software and then sending the data packet in. So now if you model that attack here or emulate that attack, you will be still able to do that same thing but with higher accuracy now. And if you have the actual hardware which is receiving the signal from polarity and then sending it back, you will be most accurate at least on the attack on that device, right? So it's just the scale and accuracy of things changing, but the algorithmic to detect anomaly or event or cyber attack is possible in all three. Just the accuracy is changing, right? Does it make sense?
Yeah, yes.
Okay. Um, so next question is that for a simple laboratory setup for test bed, can we use a laptop for carrying out the EMS and SCADA processing after receiving signal? Yeah, so you can actually have a software developed which will represent the EMS and SCADA, and you can use your laptop. Of course, it will have the limitation that how many signal you can process, and like if you have EMS, then the first thing is state estimation, then second thing is power flow. So all of these things can run if you interface that together. And now of course the power of laptop has changed so much that it was not possible 20 years before, but it is possible now if you have a powerful laptop. It will be representative behavior because like SCADA, if it's getting a signal, and if you're only doing everything in the laptop, then you will have to even generate those signal in another, either core or something that you can divide, or if you can interface with certain kind of wired USB signal or those kind of thing, you can also do that. But it will have a really small scale because processing power of laptop is still not going to be a too high. Typhoon Hill 404 model typically has a sampling rate of 250 millisecond. Are there any external data logger that can log the data at micro nanosecond level? Um, well, first thing is that I don't think that we need, I mean, even in the field, we are not doing any external data logger which is going into the nanoscale. It is all internal. So the fastest is at the not nanosecond but several nanosecond level will be power electronics, but there is no data logged from external. So I'm not sure that why it is needed at that high scale, because you will be not representing the true behavior in the field. Once you get to the micro, that also is hardly happen in the real field, right? Because the fastest data logging that happened is relay, and which is called digital fault recorder, right? Which is not at the micro level but milli, or maybe several microsecond, let's say. And that is also happening right there, right? So it's a data logger is happening. So I'm not sure that why the external data logger is needed, and even if you do that, there will be too much noise into that. So because if you use that information and feed it into somewhere else, there is some going to be communication delay and noise that will not make it very practical to run. I mean, because once we do the data logging for external, you have to use it, right? You have to process it for some application. So it will be, I mean, I can see some potential application, but I don't see that why it is needed, because it is not happening in the real power grid. Second, is it still feasible application if you have communication delay and noises, which will be definitely in milliseconds, right? or at least a fraction of millisecond. Even if you send data from one computer to another computer, it will be that much of delay. So it will be anyway, gone that nanosecond. Okay, so I think it's 9:49. Just maybe just take 2 minutes break. You can.
Yeah, sure, sir. You have a cup of tea if you want. Then we can start after 2 to 3
Okay,
minutes.
sure.
Okay, sure, sir. Thank you.
Okay.
Yes, sir. Please.
All right. So let me go back to this. So now let's talk about SCADA system and different architecture, and how do we make it redundant system so that it is more fail proof or fault tolerant. So over the years, as the computer evolved, we also had a monolithic, distributed and networked SCADA system. Now we do have a networked and distributed. So monolithic, as you can think about it, was all developed long back in mainframe computer, which means that all in one role. It's not flexible, standalone, and you cannot swap different thing in that software or those kind of things. Communication protocol RTU are very proprietary. You cannot have another RTU once it's designed and connected. And redundancy and connectivity was basically a feature of a vendor compared to possible with any vendor. In distributed, it was with LAN technology, which is networking technology, right? And then computational burden will be at a number of computer instead of one single, like which was used to be in mainframe. Server will include communication, application, user interface, and database, which is just talked about any other computing device. And redundancy was there with the server with the failover. So if one server failed, you can get to the second server, right? If this and if you want to build a third layer, then you can second, fail, then third, right? Just like typically data center work. So you have a multiple server, and same thing with the SCADA. You have a backup, and if one fails, then the same data is being reported to another backup, and you can easily switch between one and then try to fix the first one. Now, often it happens that these control center needed to do the check, because if never failure never happens, then how do you know that this failure will happen when it's needed? So you have to put sometime once a month or sometime once in 2 months these trial run that now today my EMS will run on the secondary SCADA, which is basically the backup. And then you say that we'll try it today at 10 a.m. So that need to be done so that it's getting checked. It is again vendor limitation for hardware and software. In network, it is more to distribute network. So if you remember, probably most of you were not there when we had this Windows net, transition, and that is basically networked architecture for different computing systems. It has a lot of standard protocol, the NP3, I6150, Modbus, RS232, and also implementation of wide area network. So it is typically cost effective because hardware and software become PC based. You can use the existing PC based computing to all networked and in environment that is using some kind of networked architecture to utilize more and more assets. You can easily expand, you can easily reduce, and that will if you use some protocol which is standard and anyone can know about it, then it can also cause a cybersecurity problem. And then the last one, which is basically the way we use now, which is IP-based distributed SCADA. So this is the current development. And distributed control center means like you have a multiple. It does not need to be at the same location, but multiple different room with the multiple different servers. And it is not dependent on the fixed dedicated communication, but from substation to the control room, you can easily have flexibility to change the communication, if needed, communication protocol and lines, and also some kind of backup, which means that if one link fail, then the substation A will send it to substation B, and then substation B is already connected, so it will send it to the, basically SCADA server. So some kind of redundant link, but without adding more cost, not like a double circuit, but multiple path. And then standard protocol, which allow us to use heterogeneous components, and it is a basically trade-off between the speed versus cybersecurity. So as we are advancing further and further, low cost of computer peripheral is expanding the computer communication system into it's more like an internet and intranet. We are still have the same thing, that communication is performance is getting better, interoperability is getting better, which is very important, and we are not locked in into one vendor. We can easily exchange if we find that this feature exists in vendor 2, which is needed for me. You don't need to change from scratch, only that part. And then reliability. Security is something that is still evolving. We are still trying to learn the best way to make systems cyber secure, and new vulnerability, new flag keep coming. So this is a typical architecture. So if you look at this system, you have the generation control center. We talked about like nuclear. Then you have transmission. Then you have distribution, right? And then you have these firewalls, multiple firewalls. So one is the operation control center, and then one is the ISO operation control center, which ISO is the one which has to get all the data to analyze, but they don't have any control, because they're like a secondary higher authority on utility control center. We also have to build some information flow from office intranet, which is like email and billing and all those kind of things, enterprise network, and then the EMS between the two different transmission or distribution with the primary and backup control area. So exactly has to have same copy, right? If it is not a same copy, then it will not work as a backup. So you got one key one and then one backup. As soon as this is gone or failed, you start using this one. And same thing here, then this will be reporting to the ISO. And ISO also has a backup and primary. And this is called a DMZ, which is a demilitarized zone, which means that isolated part where not everyone can get, right? And so access control is very strong, and that's why multiple firewall. And again, this is only one architecture, which will make it at least one layer of failure proof access control with a lot of firewalls between the primary control to ISO, between office intranet, which is email, billing, and everything, enterprise system to the EMS will be allowed. Process control, which is OT system, right? So it has a lot of different components. So there's a corporate network, which is again, entertaining the office work, which is like a browser of client, mail server. And if you work at utility, at least in US, you are not allowed to plug in your laptop into this. You cannot plug in. Everything that need to be plugged in this network has to be authorized by the IT person at that company. Which means that you have to allow that which IP address can connect here. And still, it's corporate network. This is not your OT system. So this is corporate, which is tied with multiple database, SAP server, mail server, and this is tied with the internet, right, with the firewall. So firewall is still allowing that who will go out and who will come in. And then we have a VPN network, which is going to the firewall penetration network. And then, with all this system, which is here, is still doing the plant network, right? So it is now getting into the OT. And then there is a additional control system application server, which is right here, which is the most protected controller and PLC and process control network on the lower side. And there will be, like maybe there's a employee who has left, or who is not happy, can install a malware directly here because they have access, right? But remote attacker with no access cannot do that. Then there's a third party who are getting this from remote access server control, and then also this contractor who is servicing our plant network might also install the hacking and malware. So you can see that even though we have made it very foolproof with a lot of these firewall and VPN connection that no one can get in without authorize, but we have to allow third party to get access. Uh, we have to allow our employee to get access, and we have to allow the third party to get access through remote access control, right? So there are some access control that is needed to keep the things operating, even the mobile operator. But that's where the problem comes, right? So you have to allow the access to fix things, to of course allow your employees so that things are working, but the same access can be used by an attacker also. um, in a control room, which is another kind of architecture. So control room, center internet, right? This is a substation. So substation have different, and the control room will have different. And then other internet, which is like enterprise control application server. Everything is a firewall, right? So you control that who will go from here to here and who will come from here to here. Corporate WAN network, and then frame relay network, which is could be radio wave dedicated line to connect these two together from substation to the control room. Within the substation, there are a lot of devices, data center concentrator, IEDs, GPS receiver, and then modem, and with the IP based control, and then another firewall which will connect to the modem to allow the uh, you know vendor and engineer to get access. But the same access can be used by the hackers too. So that's the first access control problem, which we don't know what is the solution for that, because you have to allow someone to repair, someone to monitor, someone to fix things. Wireless hub, sometime we built, again for the same purpose. And this is wired, and this is direct with the firewall. In the firewall, if I can know that, okay, I only allowed this one, and this is the only person who can get in by, let's say, whitelisting, which means that only 2 IP is allowed. It is very strict, and if the third person is needed, then we have to open that again. But then what if this hacker is somehow learned that this is the IP address which is allowed and is spoofing that IP address? Then you cannot do much. Here in the control center, you have a user interface, dispatcher, training simulator, application server, SCADA server, database server. So all of these, again, with multiple, one firewall here which will connect to the substation, another firewall here which will connect to the other internets. So this is how you isolate different network together and build more and more firewall. A lot of changes happening in the grid, as we know that high level penetration of wind power, renewable sources, demand side participation. Every time these happen, that you add a new service provider, you have to build some kind of control to use that service provider, and that control need to go all the way from where the service is to distribution system or macrogrid management system, or at least the nanogrid level, right? If not all the way to distribution and transmission. Electric vehicle, you need to control it, that how much charge we can provide, otherwise it will strain the grid. Then IDs, distribution automation, of course this big thing which is umbrella term is smart grid. A lot of this installation is happening. Now the thing is that these are the buzzword, how do we make this self-healing? How do we make it holonic architecture so it is more flexible? How do you make it cyber secure? How do you make it cyber resilient? How do you make it fault tolerant? How do you make it more robust? At the same time, we have to provide more and more connection. You have to, if you don't build any connection and say that this person can only talk to this, that's it. It's more secure, of course, right? But it's not convenient. If you want more and more service from end user, edge devices, you want to allow this vendor and third party engineer to service things and monitor things and fix things which is not failing. If it's failing, then the challenge is that how do we still keep these things, right? So that is the core thing about the security. Also, the alarm analysis diagnosis system, we want to do this data set which is coming from multiple different location, either it's an event recorder or it's a relay or it's a fault recorder or EMS, or it's even the devices which is doing the services, finally giving us data and information. But the subset here which is feeding the data is going to increase and increase with each service provider, each component that we the new component that we put in the grid. And we have to process those things to analyze the alarm, right? So first we need to see that what is the how do we know that this anomaly or not, right? That's an interpreter. And then we generalized this preprocessor, and then we use to analyze and then create the alarm and also prioritize it because there are too many alarms maybe. And then every alarm should go to somewhere else, right? I mean, if this is not controlled by operator, operator cannot do much. This is definitely controlled by operators, operator can do something. This one need to go to protection engineer, this one need to go to protection too, and then sometime this one need to go to crew member. So alarms and hypothesis is very important because something is alarm or not, who gets to decide that? Who is going to tell us that what is normal and what is not normal? And how do we know that what is normal now is also normal after 2 hours when the operating condition has changed, right? So everything is driven by this hypothesis, which is a group of engineers and grid operators and managers are going to decide that, okay, let's call this as a anomaly, this, let's call this one as an event which I want to notice and give it to the operator so that they can make a right decision. And it is a little bit tricky because we know that in the power grid my normal is keep on changing. If the load is 100 megawatt at this time, which is morning and daytime, everyone is in office here. In the evening, 100 megawatt load is not normal when people are sleeping. So if my normal is changing, then how do I decide that what should be the alarming? And which means that it need to be dynamic. It need to be dynamic behavior analysis based on this set of data that I'm getting from so many different locations. These are not complete. I mean, we have millions of data points. And we can only process few in a real time to tell that what is alarm and what hypothesis we are using for that. So that is another research. How do I decide hypothesis? What it holds in conflict? Because we don't want too many alarms, which is a conflicting alarm, which actually a wrong alarm, false alarm. Because if it happens often, that operator is given an alarm which is a false, which is not an alarm at all. Then what's gonna happen? They will see, oh, this is not an alarm that I should respond to, and they will get used to that. And if once the real alarm comes, they will say that maybe this is also wrong, and that's a wrong precedence to set up. So hypothesis alarm need to adopt with the time. Now if you look at the cascading event, it is caused by these kind of event, or it is caused by cyber attack. It doesn't matter, right? If it's caused by cyber attack, we need to train the operator for that. But most of the cascading, which is a series of events that happens to lead to a blackout, will start with only one event first. At this time, we cannot detect that is it going to lead to blackout or it's not. We don't know. But then it lead to another second event, right? And this is what happened in 2003 blackout in the US. It started with the, you know, state estimation not working, line tripped, then generator tripped, over excitation because it was providing more reactive power. Then another line tripped, and then another generator tripped with the now voltage and frequency, and then under frequency voltage load shedding happens, and that resulted into a blackout. So how do we detect this pattern? Because every time it's different. In India, when the blackout happened, 2012, it was different. In Cuba, when it happened, it was different. In Brazil, when it happened, it was different. So how do we detect which means that pattern need to be dynamic. And this is still, I would say, that open research topic, even though there is IEEE committee which is looking at the cascading events. And now the additional complexity of a cyber attack leading to the same thing makes it more complex. And then if it's something is caused by weather, then your hypothesis need to be very, very broad and still looking at all these things at how it's happening. And then if I know this pattern and I can stop some undesirable relay operation, blackout will not happen. Which is everyone wants that, but how do we detect this fundamental patterns which is dynamic? Even machine learning cannot help here. AI cannot help here because it's dynamic. Unless we have a new architecture which can look at the dynamic and adjust itself. So there are a lot of bottlenecks, inadequate exchange of real-time operation information, real-time coordination among control center. That's one problem. And when we say that, we are also talking about inadequate exchange of information between the network operation center and the power grid operation center. How much information they should share so that they will know that this anomaly and event is caused by a cyber attack. Automatic communication system, which can receive rapid and automatic information, that is missing. Communication and failure to use available communication system, that is a problem. Like I already talked about, we want alarms, but not large number. We need to prioritize and only give it to something that can. If we give a lot of alarm which no one can act on, then they do not want this. We don't want information overload. And then we also want alarm to be sent if there is a problem, right? Then inadequate transmission system security and communication facilities, which of course will be always a problem because it requires money to build more and more secure systems. Additionally, inadequate improper communication or transmission circuits, power supply failures happens also there. Standard procedure and lack of real-time operating data exchange, advanced communication equipment and emergency communication equipment. And remember that we talked about that we have to work with what we had in the past. We cannot start from scratch. If you had an older system, which is legacy system, we have to integrate the newer system, which is more secure, with the legacy system. You cannot say that just replace all the legacy system with the most secure possible. I mean, that is easy solution, but cost is so high that we can't do it. Then lack of this real-time security analysis. We don't have a way to keep running the real-time analysis and coordinated operation. So it means that existing communication information system of course lacks this coordination among various operational entities, and they send some information, but it's not full picture. And that resulted into a delayed restoration sometime because they don't know that the problem fault happens because of something in our area or somewhere else. So how does future information architecture, which we don't have it, should look like? Of course, should be more distributed hierarchical. So it can be easily, what is the advantage of hierarchical? Because if it's hierarchical and distributed, you're always doing it into a smaller area. And if some problem happens, you can just isolate that, right? And keep the remaining system. If it's not hierarchical, if everything is flat structure, then all will be impacted at the same time. It has to be fault tolerant, that, which is, uh, faults are happening, attacks are happening. How do we build some automatic control which can take care of this? Scalability, any solution that we develop, how it can be scaled up. And then, high layer for planning and operational aspects requires in hours. Sometimes even we cannot meet that in hours. And the lower layer for operational aspects, which is faster, requires in seconds, right? In milliseconds, protection in millisecond. So how do we meet those all requirement to deliver the data, which is coordinated? So protection right now is not coordinated. It will be only coordinated between 2 or 3 relays, which is okay, which is better than taking a decision without any coordination. But because of protection, most of the blackout happens. Why? It is keeping us safe, but it does not have a system view. It does not know that I am making a decision because I see a fault. But why do I see a fault? Where is the fault at the system level? And if I open it, is it going to help or not? The system. It is always helping that component where it's isolating, but it may not be helping the system. So a lot of things can be done. Some few things are redundant communication links, which requires money but is needed. Multi-protocol label switching, virtual private network, which will keep it, more private and access controlled with VPN. Local area network, IEDs, of course, is more flexible and needed. And then DMG we already talked about, which keeps the access control in the, in basically in under control. So this is another architecture, which is operation control center, corporate internet, energy trading system in the market. Very similar to what we just discussed, but now it has a newer part, ISO operating system, which is SCADA, EMS, database server. Again, another firewall here, another firewall here, another firewall here, firewall here. So the control center and corporate internet can talk. And now you'll have a backup, right? So backup will be exactly like this, but similar to the other architecture we talked about. This is one firewall to firewall between energy trading and operation center. This is the second one, which is between the corporate internet and operation control center firewall connection. And then you have a third one, which is between the ISO and operation control center. Then you have fourth one, which is basically in the power plant, which is its power plant substation kind of things. And then you have transmission substation, which is also talking with operation control center. And then you have a distribution substation, which is also talking with the operation control center, so that they can coordinate as things are happening here. Different kind of link could be different, right? So link 1 could be fiber optic and VPN. Link 2 could be metallic cable VPN. And then because these are not too far from each other, link 3 it could be also fiber optic VPN. 4, 5, 6 could be fiber optic VPN. And remember that this is a VPN is a protocol, while fiber optic is a medium, right? So communication does comes with medium protocol and all those things that we talked about, that how fast data is flowing, how much bandwidth, all those things becomes important. So in terms of control system model, we do want fault tolerance, and without fault tolerance, it will be a problem. So we can have a multiple way of building, right? Control center. So if there is no fault tolerance, of course, it will have only one information communication bus, right? If you don't have redundancy. And 2 servers with the bus connected server, where one SCADA server and one EMS database server exist, there's no fault tolerance in this, because if this fails, then there's no backup. Um, if it has one of the bus SCADA server or EMS server fails, then of course it will fail, right? It is no without backup. Substation without fault lines consists of one bus and one server. The substation connected to control center through wide area communication link, again only with no redundancy. So this is something that we don't want, but this is where we started, right? If you want more reliability, then where to put more reliability? We have to decide the asset, right? So control center server should be most important, right? Because that is what is feeding the EMS. Then next substation, if one substation is gone, of course we don't want that, but there are other substations that I can monitor still. So it's okay. Next one, substation server will be the next. If it goes down, and then in the last wide area communication link will be the last one that I'll put priority, right? So this is definitely the most important. Now, if I want to build redundancy in the system, which costs us more money but will be more cyber secure, more robust, and more cyber resilient, right? So without redundancy, we already discussed. With redundancy, we can have a one primary and one backup link, right? Only for communication. If you want computing to be redundant, then we want two bus, one main and one backup. Then we want two server, right? So a SCADA server and EMS server, and then two backup for the same thing. And then at substation also we want 1+1 and 1+1 server, right? I mean, of course, there's a lot of more money. If you want full redundancy, then UNIF design configuration 2, which is this one, and then 3 will give us enough redundancy in terms of communication and in terms of computing, right? So it's all about how much money we can afford uh, to do that. At the energy system control center level, of course we want this, but at substation maybe we don't have a lot of money, so we can avoid that no backup. If you have money, then we can build that. uh, all these cost money but will not bring revenue a lot, right? If I can save one or two blackout, then of course it's good. So it's a trade-off, that how do we decide that what is needed and how do we do that. So let me quickly change to the very briefly talk about security concept, and then I will stop, and then we'll continue on Monday. But let me just go 5 minutes over the security concept. So I see a new question, which is basically how many automation controllers may require to implement distributed hierarchical control architecture for the coordinated operation of multiple microgrid from an economic perspective. Yeah, so this question is good because it is talking about economic perspective and also redundancy. Um, of course, if we have it's a trade-off. So there's no single solution is going to work, right? So if you want distributed hierarchical control architecture, typically at least you need two microgrid controller, two communication link into that, which is economical enough but also redundant, right? Other configuration is of course only one single automation controller and one single link, which will not be redundant and cyber secure, right, or robust, but definitely economic. So cyber security and resiliency, which I think I can only do like 5-10 minutes today, but at least introduced so that you are thinking about this before we uh, dive deeper into this on Monday. Right. So in this one we're talking about cybersecurity, right? And we already talked about power grid, and we talked about the cyber infrastructure, which is sometimes we also call it information and communication technology, which is ICT, more common word in Europe. So we talked about that, what is cyber, what is power, right? And then security. Let's talk about security. So So one very important fundamental cybersecurity properties that we want to embed in the system is called CIA. C means confidentiality, I means integrity, A means availability, and it all relates to the data. So it is saying that data which is flowing into the cyber network should be confidential, which means that it should be accessible to only those people who are authorized to access it. So if I say that this should not be available to a third party or even attacker, of course, which we don't want, then it should be confidential to them. So only few people can access those set of data. And also it's a layer of confidentiality, which means some data is okay, it's public data because it's historical, and some is not. So that is confidentiality, right? So this is the most basic principle of cybersecurity. Integrity, which means that we want to guard against improper information modification, which means that data should not be modified or destructed or stopped to go where it wants to go.